Hi, everybody. I'm Kyle Carow from the National Renewable Energy Lab. We are part of the U.S. National Lab System under the Department of Energy, and I'm here to talk about ninterp, which is a crate we wrote to provide numerical interpolation with any dimensionality. I'll start off just giving some background on definitions and why I made ninterp and the research I did in the current interpolation ecosystem in Rust. All of you might be familiar with just the concept of interpolation, but I'll just go over it quickly here. Interpolation is basically data estimation between known points, and the multivariate part of it just means you can have multiple variables, multiple dimensions. You can do different strategies of interpolation here. You can see on the right, you might have like a nearest neighbor interpolation where you just pick the closest value. You might do linear interpolation where you have a linear relationship between the values. And really some real world applications of interpolation, basically any type of approximation, or for our use case, we take discrete experimental data and make a continuous model. So I'll keep going. So some motivation for an interp. The National Renewable Energy Lab has multiple modeling and simulation tools. The ones I work on are focused on transportation and mobility. So our FastSim tool is an on-road time series simulator. It generates a prediction of how much energy you use and a bunch of other characteristics. And Altrios as well is a rail simulator. It does the same thing just for trains. And for these tools, we wanted to take discrete data of, for example, like an electric motor efficiency map, which is just, you might have multiple dimensions like power and temperature or something, and then the output might be efficiency. So we wanted to take real world data and make a continuous model in code of how some component might work. And these tools have been slowly migrating from Python into Rust, probably for reasons that everyone here is familiar with, speed and reliability, etc. But one thing that we noticed was the Python ecosystem is much more mature for scientific work like this. There's existing libraries like NumPy and SciPy, etc. In Rust, there is the foundational ndarray crate as an analog to NumPy, but beyond that, it's kind of question marks in what's actually established. And we definitely needed interpolation for our purposes in these tools. So I did some digging into the current ecosystem of interpolation in Rust. I looked through some different crates here. Probably the most established is the ndarray interp crate, but none of them really checked all of our boxes. So we went ahead and developed ninterp. I won't dilly-dally on this slide too long because I have to keep moving, but we'll get into an overview of ninterp, just the basic structure of it and a quick example. So ninterp is built upon ndarray and the numtraits crates. It's effectively an extension of ndarray, but these crates give us a great deal of flexibility in the type of data we're interpolating over. And ndarray has some interesting features on working on borrowed data and owned data. So your data doesn't even have to live within the type you're using. And of course, ndarray has support for Serre, so that propagates up to ninterp. And here's the basic structure of ninterp. There are different types for interpolation. Probably the most interesting is the interp ND type. You can feed this any dimension of data and interpolate over it. But there's also fixed dimensionality interpolators, so like 1D, 2D, 3D. And these were created just because it was benchmarked that for lower dimensions, they do have a performance edge over an ND interpolator. There are multiple interpolation strategies in interp. The ones that work for any dimensionality are the linear and nearest neighbor interpolation, but there's also left nearest and right nearest, which only work for one-dimensional data. And it's pretty interesting how these strategies were structured here. The interpolation strategies are traits, and the different strategies themselves are just unit structs. And this means that you can create a custom strategy in your downstream code if you wanted to and have it use data contained in the type and everything. So there's a lot of flexibility with what you can do here. Ninterp also allows extrapolation. I'll move on to the next slide to detail that. So extrapolation is just finding a function value outside of your known data. You can see like the red dots here. You might want to predict what the blue square value would be. So there is, extrapolation support in interp. Currently, it only works for linear interpolation. You'll get an error if you try to use extrapolate enable with any other strategy here, but there are also different options if you wanted to fill with, for example, NaN values outside of your data, if you want to clamp to the data range, or if you just want to return an error. All of those are options. I'll get into a very quick example. I'll just show 2D interpolation with that fixed dimensionality interpolator, and then I'll do the same example, but with an n-dimensional interpolator. So here's the basic code. We'll just model like this 2D plane here on the right. First step is to import the prelude and then import the ndarray prelude. And interp also re-exposes this, so that might be easier to do than bringing your own dependency. And really all we do is call interp 2D new and provide our x value grid. So we have function values at x equals 0, x equals 1, x equals 2. And same thing for the y, we have 4 y values that we're evaluating over. And then the function values here that we're providing match. So this is 3 elements, this will be 3 rows, and this is 4 elements, this will be 4 columns. Next, we provide the strategy that we want to use. So if we just want linear interpolation, we use the strategy mod exposed in the prelude and do strategy linear, and then we'll just return an error on trying to extrapolate here. So exercising this, we expect that with that plane function, we should get 0.9 and at 1.5, 1.5, and that's exactly what we get. And then the second picture here is showing that if we try to, oops, my screen just locked, sorry. If we try to extrapolate the data when the extrapolate error setting was given, we do get an error as we expect. And then I'll just quickly hop over to the same problem, but using an ND interpolator. So again, we can supply probably 100 different arrays here, 100 different dimensions, but we'll just keep it to this 2D example to make it easy to visualize. So the main differences here, the coordinate grid is supplied as a single vector. It looks pretty similar to what we saw before. It's just supplied in a single vector there. And the function values you use, you just have to supply a dynamic dimension array. So if we do array.intoDyn, that's just a method given by ndarray. We'll get a dynamic dimensional array for that. And same strategy linear and extrapolate error. And of course, we expect 0.9, and we get the same exact results as we saw before. So if you would like to see more examples, there's a lot more that this crate can do, but I was a little pressed for time. There is an extensive examples directory. It shows you how to make your own interpolation strategies if you want to do that. It shows you how to swap interpolators at runtime. There's an interpolator enum. You can swap between the predefined interpolators, or you can use dynamic dispatch if you want to, or you can also swap strategies dynamically at runtime using similar enum or dynamic dispatch. And there's, of course, extensive documentation at docs.rs. So to recap, ninterp is your one-stop crate for numerical interpolation. You can use it to create continuous models with discrete data, approximate between known data, and extrapolate data beyond your known values. It supports n-dimensional interpolation, so any dimension of data that you have, you can use. And it also provides simple and performant low-dimensionality interpolators for 1, 2, or 3D data if you don't need anything fancy. And of course, you can also define the custom strategies like I mentioned. So if you'd like to contribute, the QR code for GitHub is here. PRs are welcome. I'm working on cubic interpolation, which is coming along. I just want to clean that up a bit more before I release that. But if you'd like to help out, that'd be appreciated. And that's it for me. Here's some more links. Yeah, thank you.
Thank you very much, Kyle. Very interesting talk. Does anyone have any questions? Please post them in the Q&A. Okay, we've had no questions come in. Oh, we have one come in. Cool. Taylor asks, are you fitting data via MLE or OLS, or is it user given?
This is, yeah, all user-given data. I'm not sure what those acronyms are. My background is mostly in mechanical engineering instead of software development, but I'm a REST fanatic nonetheless. But the interesting thing about an interp is the data that you provide, as long as it's an ndarray, you can provide it directly so that the interpolation type owns the data, or you can take it, you can use array views in ndarray so that you can supply it from some other struct, and you don't really need to worry about moving anything. It'll just be a borrowed version.
Gavin asks, what is a practical example for high dimensions more than 3?
Yeah, so I mentioned we model like electric motor efficiency, and this can depend on multiple things. So our simplest versions for that are just like we have an x value of power, and then we have a function output of efficiency. Usually in my work, we always care about efficiency as the function values, but it might not be power, it might be temperature, it might be for battery efficiency, it might be the battery state of charge or something. So really, there's a lot of different physical things that can affect the efficiency of a physical component. So having the flexibility to have more than 3, more than 4, more than 5 really opens a lot of doors in terms of what we can model.